everyone, it's Dr. Calkins. I'm going to talk about week 9, chapter 7 questions. This is over intermolecular forces, which is basically molecular glue. This forces that hold all things together, living and non-living. So let's get to it. Number 5 was first student submission. So number 5 says, which of the following, it says a lot of stuff, but really all that matters is highest boiling point. So don't get too wrapped up in the sentence itself. If it says highest boiling point, it just means strongest glue or forces. Our strongest glue is hydrogen bonding. Hydrogen bonding is when you have the 3 most electronegative atoms, nitrogen, oxygen, and fluorine, attached to hydrogen, which is the least electronegative nonmetal that we really deal with in class. So here we see a NH, that's hydrogen bonding. We see an OH, that's hydrogen bonding, at least hydrogen bonding capable. The bond O to H is not hydrogen bonding, but its ability to attract other molecules like it is. And just like beneath it, the slightly larger version with 1 extra carbon, this is ethyl versus methyl. Also hydrogen bonding. So we have a 3-way tie. Definitely we can get rid of methane. That's going to be dispersion forces only because it's a hydrocarbon. So if this question said lowest boiling point, that'd definitely be the winner, but it didn't. So now we have a very small ammonia or larger methanol, methyl alcohol, or larger ethanol or ethyl alcohol, and we definitely want the biggest piggy wins when there's a tie, unless you're comparing yourself to water, and we're not. So there's that one. Now we need to look at number 6 under the very same kind of lens, SO2. If we draw it, it's a rule breaker, so it's a little tougher to draw, but I'll cut to the chase at the same time. Here's your structure. It is a bent 118 kind of structure. We want to know if it has Lennon forces. Well, all things have Lennon forces. All things have electrons. So check. They want the dominant force though, so we want to know, do they have dipole forces? To have a dipole force, you need to have the 0.5 or larger polarity, so let's look. Sulfur is a 2.5, oxygen is 3.5, that's a 1.0 difference. So you have a 1.0 towards oxygen, you have a 1.0 to oxygen. That's not a 2-way tie because it's not linear. So it does have dipole forces. Does it have hydrogen bonding? Well, you have to have N to an H, O to an H, or F to an H for that to happen. That's our 3 biggest bullets attached to hydrogen, and we don't have hydrogens or nitrogens, oxygens, or fluorine, so it doesn't apply. Van der Waals force is basically all of these. That's just the scientists associated with their discovery, or at least their interpretation. So don't worry about that, that's just there to distract you. So dominant force is definitely the stronger one. Dipole forces are like our motorcycle, Lennon forces are like our tricycle. So dipole forces are the more powerful, about 8 times stronger. Look at number 7, they say hydrogen bonding again. Well, we already know that definition from up here. So look for those NHs, OHs, or FHs. We see an OH here. Alcohols are great for hydrogen bonding. Just for practice, here we have a hydrocarbon that's going to be dispersion forces only because it's nonpolar. Carbon to hydrogen is 2.5, 2.1, that's a 0.4. We need to be 0.5 or larger to have a dipole. Same issue here, dispersion only. And again, only because they don't have any covalent bonds. All 4 of them have dispersion forces, but again, those 2, that's all they have. This one has dipoles, it has dispersion, but it also has hydrogen bonding, that's what really matters. It's got the Ferrari of forces. Methyl chloride does have this carbon, which is 2.5 to chlorine 3.0, so that's a dipole of 0.52 from the carbon to the chlorine. So that is a dipole force, but it's still not hydrogen bonding. So again, see the answer. All right, as we get to the next page, nonpolar molecules, they have what everybody has, and that's Lennon forces, which is just a fancy name for dispersion forces. We said London Bridge is falling down. It's kind of a good analogy because dispersion forces are always breaking. And if you're non-polar, that's all you have. You have the tricycle sitting in your garage, nothing else. Not very powerful. Polar molecules, though, they have London forces because everything does. Polar molecules can have dipoles if 0.5 or larger, and that would be the criteria for being polar in the first place. And then very polar molecules can have hydrogen bonding, so all the above. Just remember, hydrogen bonding, you need to be the three biggest bullies: nitrogen, oxygen, fluorine attached to hydrogen. So that's 3 examples of where it could fit into that category. 15 says, what is the strongest London forces? So if you're tied, use size to break your tie. Water is H2O, helium is He, hydrogen is H2, the gas molecule, and carbon tetrachloride is CCl4. So hydrogen is 1, oxygen is 16, another one's about 18. Helium's only 4, so definitely water winning so far. Hydrogen would be 1 plus 1, which is 2, so water's still winning because it's still the biggest. It's got the most electrons, the most, the largest snow globe in our analogy from lecture. But then if you're carbon, you're 12, and then if you're 4 chlorines, you're 35 each, so there's 140, and then plus another 12, so gigantic, and the winner. It's going to have the biggest snow globe because it has the most electrons. If it has the most electrons, it's going to have the biggest or the easiest ability to disperse and have some kind of attraction to one another. 16. Main reason why carbon tetrabromide is a solid is because it's big. Carbon tetrachloride that we saw a moment ago is not as big, so it's a liquid. Because they're both 4-way ties, carbon tetrabromide wouldn't even really matter because it's only a 2.5 to 2.8 electronegativity. But in any case, their shape is going to cancel any dipoles, and then it's just going to be back to use size to break the tie. And carbon tetrabromide is bigger. So real quick, if you have 4 chlorines, that's 435. If you have 4 bromines, that's 4 at about 80. So it's much, much bigger to have bromines. So bigger snow globe effect. Number 17, largest dipole. To have a large dipole, you need to not cancel out like nitrogen. Nitrogen has got a triple bond between it, and even though it's a big bully, when it's attached to itself, it has no dipole. Hydrogen is H to H, no dipole there, they're going to cancel. Methane is CH4, that's a hydrocarbon, and carbon is a 2.5, hydrogen is a 2.1, that 0.4 difference is not enough for a dipole, we need 0.5 or larger. Acetone being the winner, acetone is a ketone. That carbon to oxygen is 2.5 to 3.0, that's 3.5. That's a dipole of 1.0. So 1.0 is definitely a strong dipole. All carbonyls have them, like aldehydes, ketones, esters, acids, and amides. Number 18. There's a picture of this in the notes, but an OH bond. This is a polar covalent bond, and it's worth 400 kilojoules. I'm not going to break those, not easily. But in 19, when it says the strength of a hydrogen bond, we said that's only 16. So here's the answer for hydrogen bonding strength compared to, say, the actual covalent bond that's polar. But they're saying percentage, so what is, how many 16s is in 400 basically? And that's only about 4%. So the biggest misconception about this is students like to think O to H is hydrogen bonding, but that's a polar covalent bond of shared electrons. Hydrogen bonding is an attraction between 2 separate molecules. So watch out for that. Hydrogen bonding is not a real bond, it's a attraction. Moving along, lowest boiling point. We want weakest forces. So look for the hydrocarbon, and there's ethane there. These have hydrogen bonding, so stay away from those. Those would be highest. This one has oxygen, it has dipoles towards oxygen. And so dipoles there, hydrogen bonding there. So definitely this is going to be the highest. These guys are going to be in the middle. This one's still higher. And then the lowest is going to be the nonpolar hydrocarbon. 21 says highest, so look for strongest forces. And definitely OH, NH, FH, definitely those are hydrogen bonding. Biggest dipole there of 2.1 to 4.0. So hydrogen bonding the winner always for strongest. HBr, not even, barely polar, 2.1, 2.8, 2.1, 3.0, 2.1, 2.5, so not even enough to be polar there. So look at electronegativity. All of those numbers that we need to subtract are in this right side corner. Lowest boiling point, so back to weakest forces. So what's unique about these is what we'd expect. I'm going to just draw a quick little graph over here. We expect something like this: H2O, H2S, H2 SE, and H2 TE. So this would be boiling point, and this would be size. We expect that to increase because if you're bigger, you're harder to pick up. Gravity is going to pull you stronger. Problem is, when you're super polar like water, you're through the roof, and it's going to have the highest. So the answer is going to be the next lowest, and that's H2S. Because H2S is not polar, 2.5, 2.1, and because it's not water. Water is super unique for that reason. So that's a tricky one. Covers two concepts at once. Number 23, a little bit easier. To be ionic, you have to have a metal. Sodium's a metal, magnesium's a metal, potassium's a metal. This is not ionic, so ammonia is NH3, all nonmetals. So a little bit easier there. 25, how does any antibiotic attach to bacteria? Through glue. And the glue that we want is the one that interferes with cell wall construction. So antibiotics' job is not to kill bacteria, but to stop it from growing. So your white blood cells can do what they're supposed to do. They were losing the battle, antibiotics help slow down the war so that they can catch up and start winning. Number 26, how does it work? How does it attach to bacteria? And that's through the strongest glue. That's why antibiotics are effective, because they have strong glue that has to be broken. So hydrogen bonding always. See that in the notes as well. Melting and freezing points are identical. It's a two-way street. We saw that back in chapter 1 even. So that's true. Attractive forces between carbon dioxide are stronger than those in water. Carbon dioxide, C double bond O on both sides. This is the two-way tie. It's got a 1.0 here, and it's got a 1.0 there. So those cancel. So it does have maybe stronger dispersion forces because it's larger, but water is the bent H2O molecule, and it's going to have 1 point force when you compare the 2.1 to the 3.5s. So definitely there, false. Water is going to kick carbon dioxide to butt with forces. It's got the Ferrari, and carbon dioxide has the tricycle. So 30, polar molecules do not exhibit London forces. That is false, because everything exhibits London forces, polar molecules included. It's just that if you're polar, you have the motorcycle and potentially the Ferrari if you have the right kind of polarity, and nobody cares they have the tricycle still. But it's still there, still contributes a little. Number 31 says, what's the reason why water has a higher boiling point than acetone? And that is because we do have the hydrogen bonding of water. So, true. And lastly, this is in the notes, replacement of one NH group, which is one hydrogen bonding site. Makes vancomycin 1,000 times less effective. So if it takes 1,000 more hours to feel better, that's pretty ineffective. So true. Vancomycin has 5 hydrogen bonding sites. If you take away one, it's not going to glue as strongly, so bacteria is going to continue to grow. It's not going to be antibiotic resistant. Almost done. This section here, students had trouble with, so let's just give you a quick rundown of how it works. To be metallic, you just need to be a metal on the periodic table. London forces, You need to be nonpolar. Again, everything has them, but nonpolar is where it matters for our homework. Covalent networks are things like diamond, graphite, and quartz. Those are covalent bonds. So you're breaking the actual covalent bond that's worth 400 kilojoules, not the hydrogen bonds that are worth 16 and the dipoles that are worth 8, or the dispersion forces that are worth 1. And then hydrogen bonding, lastly, is the NH to OH to FH bonds that are superpolar. So definitely you see one of those there. Hydrogen fluoride exclusively. Quartz is one of the examples we said watch out for. Methane is a hydrocarbon, CH4, so London forces. Iron is a metal on the periodic table. Carbon tetrabromide also, lots of nonmetals, so lots of London forces. Then lastly, this was the end of our lecture. Molecular just means all nonmetals. And non-molecular just means not all nonmetals. So you're going to have a metal and nonmetals together, typically as ions. So look for metals like sodium and aluminum, and those are non-molecular. Look for things like NH3 that are all nonmetals to be molecular, and carbon tetrachloride molecular. So that wraps up this chapter. We'll see you next time. Keep submitting questions through discussion forums.